Hello again, astronauts! Today, we'll be discussing a recent, super exciting breakthrough in nuclear fusion research. Nuclear fusion, the process of atoms combining and releasing energy, powers stars for billions of years. If we could efficiently replicate reactions on Earth, combining hydrogen atoms, the most common element in the universe, into helium, we would have an effectively unlimited source of clean energy, and all of our current energy issues would be meaningless. Fusion energy could be the silver bullet which allows us to fix climate change, energy shortages, and make your crush confess their undying love for you. But nuclear fusion usually happens in the cores of stars, under intense heat and pressure. Replicating those conditions on Earth is incredibly difficult, expensive, and energy-consuming. So much so that all previous attempts to cause fusion reactions, even successful ones, have consumed more energy than they put out. And if you can't get net positive energy from your fuel, it's not a viable energy source. So while hydrogen fusion holds a ton of theoretical promise, it was an expensive research project with little likelihood of short-term reward. Excuse me, who are you? I'm Sharon's friend. Did you really think you could do a nuclear energy follow-up without me? Well, Eris has only mentioned Sharon Noble to me, but didn't mention her friend. Where have you been this whole time? The void where self-aware fictional characters live between scripts. It's been a while because Eris didn't want to bring me out for some reason. Do you think I'm overdone? That's not true. You probably just weren't a great fit for any of those other scripts. But I did a great job in the last nuclear energy video. I've already done all of the background research, and I am the most qualified for this position, so why am I being shafted here? Well, she usually uses you for more controversial topics, where you can be angry and debate Sharon as an allegory for the controversial topic at hand. Oh, so now that you have a nuclear energy story, which probably won't make people scared or angry, you don't need me anymore? Yes. So you're happy to use the stigma surrounding BDSM and sex work as a visual metaphor for other controversial topics, but you won't do the work to provide representation even when I'm the most qualified character for the job? No, I don't think that's acceptable. Are you sure you can handle delivering good news? You've never done that before. But on December 5th, 2022, at Lawrence Livermore National Laboratory's National Ignition Facility in California, a facility which began construction in 1997 and operations in 2009, finally achieved the milestone of ignition, where they got more energy out of the reaction than was put in. This is a huge deal because it proves that commercial nuclear fusion on Earth, while still decades away, is possible. It appears I wasn't clear. This is my video now. Leave. That was not a request. Yes, ma'am. So let's talk about what nuclear fusion is, why it took scientists decades to reach this goal, what this experiment looked like, and what the future holds. Welcome to Bad Astra. Where we talk about space, physics, and combat science misinformation with more costume changes than math. I'm Astra. I have a BA in physics, a master's in mechanical engineering, And I'm back in this costume because you all seem to like this character. Eris, a chaotic witch and our writer, is responsible for me coming back more often. My wife, Nova, is the smart one and is finishing up her PhD in astrophysics. She's not only the science consultant on our physics videos, but designed our logo. Thank you so much for watching our videos, and we'd really appreciate it if you like, subscribe, and leave a comment down below. I read them all and try to respond to most of them. If you really love our videos and want to support us paying for increasingly elaborate costumes, props, locations, and filming equipment, we have a Patreon where you can sign up to get early access to all our videos, behind-the-scenes updates, blooper reels, and other fun perks. Before we get into this experiment, let's answer some quick questions. Don't we already have nuclear power? What is nuclear fusion? And why is it different from regular nuclear energy? There are two types of processes that produce nuclear energy. Fusion combines or fuses atoms to release energy. Fission is the opposite, where atoms are split apart to release energy. Now, if every atom was capable of doing both, it would literally break physics. We know that for atoms smaller than iron, fusion releases energy, while for atoms larger than iron, fission releases energy. The math reasons for why that is are beyond the scope of this video and are left as an exercise to the viewer. Regular nuclear energy, or fission, involves large, unstable, or fissile atoms, usually uranium-235 or plutonium-239, getting hit by neutrons and splitting apart, releasing energy and more neutrons, which split apart more atoms, in a chain reaction called runaway fission. Because neutrons are everywhere, all we need for a self-sustaining fission reaction is a critical mass of fissile material. Non-trivial, but doable. I highly recommend checking out my previous video on nuclear physics to learn more. Fusion reactions, on the other hand, happen when atoms lighter than iron combine to release energy. Hydrogen is the lightest and most common element in the universe, and the fusion reactions of hydrogen into helium are what powers stars. The fusion reaction of hydrogen to helium per atom also releases far more energy than the fission of a uranium atom. Since hydrogen is more common, not dangerously radioactive, and releases more energy, why don't we have hydrogen powering cities yet? Well, unlike fission, which just needs a critical mass, fusion requires a lot of heat, pressure, and luck before it's possible. The centers of stars are incredibly hot and dense, full of ionized hydrogen, or protons, moving around really fast while confined in an incredibly tight space. Protons are positively charged, so they repel each other. To fuse, the protons have to be moving super fast towards each other so that the slowing force of their repelling charge doesn't stop them from colliding, and they get bound together by the strong force, or the force that binds an atomic nucleus together. But not even the high heat and pressure in star cores can provide enough energy to overcome the Coulomb barrier. So, according to classical physics, protons should never collide, and fusion is impossible. But fusion is what powers stars, and stars exist, so yeah, it makes no logical sense. And whenever small things are making no logical sense, you just know quantum mechanics is involved. Heisenberg's uncertainty principle states that the more you know how fast something's moving, the less you know where it is, and vice versa. And by we, Heisenberg meant that the universe itself doesn't know. But while a particle's exact location and speed are uncertain, there is a relative probability of where the particle is and how fast it's moving. And the most logical place for the particle to be is also the most likely. The proton is most likely outside the Coulomb barrier of the neighboring proton. Juliet is up on her balcony, Romeo's down below. But Quantum mechanics knows about a secret tunnel for Romeo.
Secret tunnel! Secret tunnel!
The wave function just tells us where Romeo is most likely to be. Sometimes our Romeo proton just pops up behind the Coulomb barrier. The universe thinks Romeo's almost definitely outside, but Romeo's inside the Capulet household and fusing with Juliet as we speak. The entire fusion process involves way more steps than this, which I went through in exquisite detail in our original nuclear energy video. For now, you just need to know that for fusion to happen, even in rare, lucky instances, the protons need to be incredibly hot and under an incredible amount of pressure. Like Nova applying to postdocs.
Hey, Nova, you should probably eat something. Okay.
Now that we know how much more difficult nuclear fusion is than any of our current energy sources, why is it worth so much time and effort to research? Are these researchers just pursuing science for its own sake? Like CERN, replicating conditions of the early universe and smashing particles together to learn more about particle physics. Are scientists recreating the condition inside cores of stars to learn more about nuclear physics? While I personally believe that goal in itself would be worthwhile, scientific inquiry and knowledge for its own sake is more than enough for me. These experiments have a stated future application which could revolutionize our society. For decades, scientists have known that hydrogen fusion, the origin of all sunlight and starlight, could provide a limitless clean energy source. No more pollution from coal plants and car exhaust. No more greenhouse gas emissions from fossil fuels. No more radioactive nuclear waste. Far fewer resources than solar or wind. All the cheap energy anyone could ever want with zero carbon footprint.
Julio Friedman, chief scientist at Carbon Direct and a former chief energy technologist at Lawrence Livermore, says, unlike coal, you only need a small amount of hydrogen, and it is the most abundant thing found in the universe. Hydrogen is found in water, so the stuff that generates this energy is wildly unlimited, and it is clean.
Fusion projects mainly use deuterium and tritium, isotopes of hydrogen with 1 or 2 neutrons respectively. Starting with the deuterium in this glass of water and just a little tritium, fusion could power a house for a year. Tritium is rare, but if you can't find your own, synthetically made in a lab is fine. So why aren't we funding this? Well, we are. Fusion research around the globe has received huge amounts of public and private funds for over half a century. $5 billion has been invested into fusion startups just in recent years, due to the urgency of clean energy solutions because of the climate crisis.
Michael Campbell, former director of the Fusion Laboratory at the University of Rochester and an early proponent of the National Ignition Facility, or NIF, while at Lawrence Livermore Lab, reminds us, fusion research has been going on since the early 1950s, and this is the first time in the laboratory that fusion has ever produced more energy than it consumed.
It's basically impossible to recreate the core of a star in a lab. The way NIF scientists planned to recreate the core of a star in a lab was to take a tiny ball of frozen hydrogen encased in diamond contained in a pea-sized gold cylinder and shoot it from all sides with 192 of the most powerful lasers they could possibly build. That experiment, which finally achieved ignition, was a quarter of a century in the making. NIF is an experimental facility the size of 3 football fields, part of the U.S. Department of Energy's nuclear weapons program, designed to study thermonuclear explosions. With $3.5 billion from the federal government, construction began in 1997, Operations commenced in 2009, and the original goal was ignition by 2012. But, like JWST, which we covered in a recent video, NIF also experienced significant delays and cost overruns. In the beginning, the facility hardly generated any fusion at all. After 5 years, in 2014, a successful experiment yielded enough fusion energy to power a single 60-watt light bulb for 5 minutes. Considering how expensive each laser shot was, the facility was understandably criticized for its lack of progress in the following 7 years. But in August 2021, NIF scientists got close to ignition once, getting 70% as much energy out as they'd put in, but were unable to replicate the success. But they knew they were on the cusp of ignition.
According to Dr. Mark Herman, Program Director for Weapons Physics and Design at the Livermore, once you get close, little changes can make a big difference.
So, the scientists improved the hydrogen target balls to have fewer imperfections, adjusted how they delivered the laser blast to ensure it was even from all angles, and increased the energy of the X-ray lasers by around 8%. In September 2022, the first laser shot, really 192 lasers shot at the same time, at the increased power hit the tiny hydrogen target with 2.05 megajoules, the equivalent of a pound of TNT. That first try produced 1.2 megajoules of fusion energy, more than half of what was put in, but still not enough to break even. After analyzing the data, the scientists figured out that they hadn't squeezed the hydrogen evenly, so some of the hydrogen essentially squirted out the side and never reached fusion temperatures. That wasted kinetic energy from the imperfect alignment had cost them ignition. So they made even finer adjustments to create that perfectly spherical implosion.
The fuel capsule is a BB point-sized shell made of diamond that needs to be as perfect as possible, Michael Statterman, Target Fabrication Program Manager at Lawrence Livermore National Laboratory, says. As you can imagine, perfection is really hard, and so we've yet to get there. We still have tiny flaws on our shells, smaller than bacteria.
Because this experiment requires basically compressing a basketball into the size of a pea in under a nanosecond while keeping it perfectly spherical, symmetry of both the lasers and the capsule are incredibly important. So, at 1:03 a.m. on December 5th, with 192 of the world's most powerful lasers trained on a pea-sized gold cylinder containing a frozen pellet of hydrogen isotopes, deuterium and tritium, encased in diamond, they took the shot. The laser beams entered at the top and bottom of the cylinder, vaporizing it and generating an inward onslaught of X-rays, compressing the BB-sized fuel pellet of deuterium and tritium. In less than 100 trillionths of a second, 2.05 megajoules of energy from all sides crushed the capsule, heating it to over 3 million degrees Celsius, temperatures only seen in stars and thermonuclear weapons. With the right conditions met, some of the hydrogen isotopes tunneled and fused into helium, releasing more energy, causing a cascade of fusion chain reactions and releasing neutrons carrying 3.15 megajoules of energy. For those keeping track at home, that's not just more than double their previous record, but 54% more energy than was put in. Livermore, we have ignition. 4% of the fuel pellet was converted to energy.
Dr. Mark Herman reflected, the prediction ahead of the shot was that it could go up a factor of 2. In fact, it went up a little more than that.
Other researchers around the world are pursuing different fusion experiments. Lasers at different wavelengths might heat the hydrogen more efficiently, for example. And shooting hundreds of lasers at a hydrogen target hasn't been the only method tried. Different reactor designs around the world have been built in the attempt to both generate fusion reactions to release energy and capture that energy to turn it into usable electricity. Until recently, All those experiments have consumed more energy than the fusion reactions generated. The most common experimental design hasn't actually been shoot a small thing of hydrogen with lasers, but donut-shaped reactors called tokamaks, which are a lot cheaper to build. Magnetic fields trap hydrogen gas inside the donut, where it's heated to extremely high temperatures, enough to separate or ionize the atomic nuclei from their electrons, turning hydrogen gas into plasma. These protons are now incredibly hot and under intense pressure, similar to the conditions at the cores of stars. The superheated protons are trapped together and now have enough kinetic energy to get close enough for some tunneling events to randomly occur. A little fusion happens, and energy is released in the form of neutrons flying outwards. However, no tokamak has ever created enough fusion reactions to reach ignition or put out as much energy as was put in. However, because of the experimental design of magnet-contained plasma, tokamaks could potentially sustain fusion reactions for much longer than a single laser pulse lasting a fraction of a nanosecond. The ITER project, a $22 billion collaboration between China, the EU, India, Japan, Korea, Russia, and the United States, aims to achieve self-sustaining fusion using this magnetic containment method. ITER will keep a plasma of deuterium and tritium, hydrogen with extra neutrons, confined in a toroidal or donut-shaped vacuum chamber and heat it up until the nuclei fuse. Operations are set to begin in 2035, with the goal of reaching the burning stage, where the dominant source of heating is from the reaction itself, so the reaction is self-heating and self-sustaining. Even though lasers and magnets are two different approaches, breakthroughs in research for any fusion reactor design, be it laser fusion or magnet fusion, can help researchers everywhere improve their own designs, bringing commercial fusion power closer. Nuclear fusion ignition is a huge milestone in the quest for commercial fusion power.
At a DC press conference announcing the news, Jill Harubi, the National Nuclear Security Administration administrator, said, Monday, December 5th, 2022 was an important day in science. Reaching ignition in a controlled fusion experiment is an achievement that has come after more than 60 years of global research, development, engineering, and experimentation.
Translation: oh my god, we did it! It took us 60 years, but we did it! Ah!
Still, the NIF experiments focused on fusion energy absolutely are valuable on the path to commercial fusion power, says Ann White, a plasma physicist at MIT.
Translation: we might actually be able to make fusion power available to solve climate change. This is so huge! Oh my god!
This is such a wonderful example of a possibility realized, a scientific milestone achieved, and a road ahead to the possibilities for clean energy, said Arati Prabhakar, the White House science advisor, and even deeper understanding of the scientific principles that are applied here.
Translation: listen, I'm not saying that scientists are the coolest people ever to exist, but they literally made something seemingly impossible happen.
This is very important because, from an energy perspective, it can't be an energy source if you're not getting out more energy than you're putting in, said Dr. Julio Friedman. Prior breakthroughs have been important, but it's not the same thing as generating energy that could one day be used on a larger scale.
Translation: y'all don't understand how big this is. Like, you thought previous scientific discoveries were massive? Think again. Einstein? Who? Newton? Where? Bacon? Cooked. Okay, I think I can handle the translations now. Okay, go for it.
This is a landmark achievement for the researchers and staff at the National Ignition Facility who have dedicated their careers to seeing fusion ignition become a reality, and this milestone will undoubtedly spark even more discovery, said U.S. Secretary of Energy Jennifer M. Granholm. The Biden-Harris administration is committed to supporting our world-class scientists, like the team at NIF, whose work will help us solve humanity's most complex and pressing problems, like providing clean power to combat climate change and maintaining a nuclear deterrent without nuclear testing.
Translation. You want more of this cool shit? Give us more money. We know that the Republicans won't, since they're too busy building expensive jets and shit for the military. So, if you want this cool shit all the time, fund us for fuck's sake.
We have had a theoretical understanding of fusion for over a century, but the journey from knowing to doing can be long and arduous. Today's milestone shows what we can do with perseverance, said Dr. Arati Prabhakar.
Translation. Literally, this took us forever. You know why? Because we weren't given all the resources like other less cool programs were. So, we managed to do this out of sheer determination and spite.
Monday, December 5th, 2022 was a historic day in science, thanks to the incredible people at Livermore Lab and the National Ignition Facility. In making this breakthrough, they have opened a new chapter in NNSA's Stockpile Stewardship Program, said NNSA Administrator Jill Harubi. I would like to thank the members of Congress who have supported the National Ignition Facility because their belief in the promise of visionary science has been critical for our mission. Our team from around the DOE national laboratories and our international partners have shown us the power of collaboration.
Translation. Thank Newton that some people actually want to solve the world's most pressing issues. See what happens when we put our massive egos aside to actually work together instead of causing massive government shutdowns because you're too busy throwing tantrums? Clearly, some people didn't learn anything from being forced to do group projects in school.
U.S. Senate Majority Leader Charles Schumer says, making this future clean energy world a reality will require our physicists, innovative workers, and brightest minds at our DOE-funded institutions, including the Rochester Laser Lab, to double down on their cutting-edge work. That's why I'm also proud to announce today that I've helped to secure the highest ever authorization of over $624 million this year in the National Defense Authorization Act for the ICF program to build on this amazing breakthrough.
Translation. Clearly, this is more important than whatever bullshit tax breaks for the 1% are doing, so I'm going to give more money to the people actually making the world a better place. Unlike some assholes who decide that letting Elon Musk get more money to fuck up Twitter or whatever was a good idea. Not the translations I would have gone with, but you've got the spirit. The cynical part of me thinks that the most important part of this breakthrough is the increased attention and acclaim for this research. Loads of other congresspeople are using this moment to call for increased funding for this research. And alongside gravity, electromagnetism, strong and weak, the fifth fundamental force of physics is funding. This is fantastic. You know what? You did deliver good news well. We've reached an incredible milestone in the magical energy source which will fix climate change. Oh no, this won't fix climate change. And there it is. Can't you just be optimistic for once? Our leaders appear to be rallying around with funding for more research. Science is winning, and with the right investment... No. Fusion alone doesn't have a chance of fixing our current climate crisis. To pretend it does isn't just optimistic, it's willfully misleading. Give me one good reason why it can't be the solution. And you can't say capitalism. Time. We're too late. Even if we doubled the funding of everyone studying fusion tomorrow, which I'm not against, these experiments take a lot of time. Time which we don't have. Solar, wind, hydropower, and fission nuclear power are already commercially available. If we throw money at those, it's going to be a lot more effective right now. But we got more energy out than in. That means if we just replicate the experiment a ton of times, it could provide energy for the grid. No. First of all, the National Ignition Facility was not designed with commercial fusion energy in mind, but for experiments to help the United States maintain its nuclear weapons. NIF averages only 10 laser shots per week. A commercial facility using the laser fusion for energy would need to be able to do closer to 10 shots a second.
Dr. Kimberly S. Boodle, the director of Lawrence Livermore, said, "This is one igniting capsule, one time. And to realize commercial fusion energy, you have to do many things. You have to be able to produce many fusion ignition events per minute."
Second, these lasers aren't efficient, just the biggest lasers they could possibly build. NIF is the world's most powerful laser, but it is a slow and inefficient one, relying on decades-old technology. While only 2.05 megajoules was delivered to the target, NIF's 192 lasers consumed 322 megajoules of energy from the grid in the process of creating that laser blast. So overall, the experiment didn't create close to break-even energy.
Even with a more efficient rapid-fire laser, Dr. Herman estimates you'll need gains of 30 to 100 in order to get more energy for an energy power plant.
Third, we currently have no way of using the energy produced. The machinery to harvest the energy released in the reaction and turn it into electricity, which can be deployed to the power grid, hasn't been developed yet. The energy-carrying neutrons also put a tremendous amount of stress on the equipment creating it, slowly destroying the fusion reactor itself.
Dr. Ann White, head of MIT's Department of Nuclear Science and Engineering, points out that neither the US or UK-based projects have the hardware and steps in place to convert fusion neutrons to electricity.
What NIF made is closer to a tiny, expensive H-bomb than a sustainable fusion reactor.
As Dave Hammer, a nuclear engineer at Cornell University, says, "It's a big milestone, but NIF is not a fusion energy device." Stephen Bodner, a physicist who formerly headed the laser fusion program at the U.S. Naval Research Laboratory, says the big question now is what the DOE will do next: double down on weapons research at NIF, or pivot to a laser program geared towards fusion energy research.
Well, that was a depressing dose of reality. You were getting too happy and therefore too annoying. So, what's next for fusion energy? Is it worth pursuing if it can't fix climate change? Yes! I said it couldn't fix the current climate crisis alone. I didn't mean it's useless. I meant we still need transition fuels. But with the right investment, it could potentially be a lower-cost, permanent solution. So the transition fuels are like the entry-level job you get right out of college so that you don't starve, and fusion could be that dream job you get after building your career? Okay, what do we say about career building and dream jobs? Career building is a myth, perpetuated on the belief that we live in a meritocracy instead of a nepotistic boys club that is fully reliant on charisma, satisfying egos, and not being part of a minority group for upward mobility, instead of basing promotions solely on talent and ability to do the job. And I shouldn't dream of labor because my worth as a person is not based on my ability to be productive in a capitalistic hellhole that is designed to exploit everyone except those at the top. Exactly. Otherwise, your analogy was fine. Fusion is still at least a decade, probably decades, away from commercial use. The good news is that this development has been touted by the Biden administration as an affirmation of a massive investment in fusion by the government over the years. And the Biden administration is prioritizing fusion energy research in its climate and energy agenda. The White House held a summit in March seeking to accelerate commercial fusion efforts. President Biden set a 10-year goal of a commercial fusion reactor by 2032. Fusion projects are in the front of the line for tens of billions of dollars in subsidies and grants, authorized by the Inflation Reduction Act, Biden's climate package. Wow. Somehow politicians are worse at naming things than physicists. To demonstrate that laser fusion can be a viable way of producing energy, the three issues I mentioned earlier need to be fixed. First, researchers need to dramatically increase the rate at which lasers can fire shots, and how quickly the target chamber can be cleared and prepped. 2, the energy released as a percentage of the energy put into producing the laser pulses needs to be at least 100 times greater. And 3rd, we need an energy collection method. Accomplishing these 3 milestones would be huge. So how long before we have commercial fusion energy?
Dr. Butel estimates probably decades. Not 6 decades, I don't think. I think not 5 decades, which is what we used to say. I think it's moving into the foreground, and probably, with concerted effort and investment, a few decades of research on the underlying technologies could put us in a position to build a power plant.
Another issue is cost. Remember that the hydrogen pellets must be perfectly symmetrical spheres? Perfection is labor intensive. A single target pellet might cost about $100,000 today, according to University of Chicago theoretical physicist Robert Rosner. That cost would need to drop to pennies for a commercial fusion reactor using 1 million pellets a day. So why are we even celebrating this achievement if we're probably still decades away from commercial fusion and we need to transition away from greenhouse gases a decade ago to stop climate change? Because commercial fusion ever, especially if it's in my lifetime, is something to massively celebrate every step along the way. And this is a major step.
As Dr. Gianluca Sari, a physics professor at Queen's University Belfast, puts it, we got to the top of the hill. We hit the hardest milestone, we can see the beautiful view on the other side. Now, we have a long walk to get to that beautiful place in the distance. But it's all downhill. Dr. Omar A. Hurricane, chief scientist for the Inertial Confinement Fusion Program at Lawrence Livermore, explains, what remains to be done from here is largely engineering, of increasing the laser energy efficiency and increasing the target energy gain with further target optimizations.
And I'm choosing to be optimistic, so I'll follow the lead of Tony Rolstone, a fusion expert from the University of Cambridge's Department of Engineering, who pointed to a piece of nuclear history. In 1942, Chicago scientists ran the first ever fission nuclear reactor for 5 minutes in its first run. Only 15 years later, the first US-based nuclear power plant went online in Pennsylvania. Science is a process, a slow but shockingly fast process. Astra's out.
Ad Astra, to the stars, to the stars.